First of all, of course, these all came from the exam. Describe these as endothermic or exothermic, the formation of dew in the morning. These all also, by the way, came from widely missed questions, so questions that a lot of people missed. What about dew? Is it endothermic or exothermic? It's exothermic. You're going from water vapor in the air to water liquid on the leaves. So vapor to liquid releases heat. Vaporization of water is the opposite of that, right? It takes energy, you have to put energy in, and then it becomes vapor. All right, this one, when 280 mLs of that concentration hydrochloric acid is added to this, which, if any, is left over? How many moles are left over? Now, this one on the exam was a multiple choice question, if you remember, that asked if the resulting solution was acidic, basic, neutral, or you can't tell. But this is, in effect, what it was asking. I sort of made it a little easier for you. Which one is left over, and then how many is left over? So what you have to do, what? So what you have to do is find the moles of, well, you need the equation first. So it's going to be 2HCl plus magnesium hydroxide yields water plus magnesium chloride. Which reminds me, one of the things that I was most concerned with, that I was very concerned with on the exam, was people still not knowing symbols for elements and ions. I didn't put anything too crazy or tricky. I didn't make you come up with the symbol for rhenium or something, but you know, people not knowing that potassium is K or that magnesium is +2, some of these things that we've been doing over and over again for a long time and that was supposed to really be a prerequisite for this class, that's a little bit troubling. So please, you are already too late if you haven't gotten all those yet. Please, please, please work on those. All right, so you had to figure out the moles of each of these by multiplying the volume times the concentration. No. Well, I mean, yeah, yeah. That's how you figure, not that equation, but it's concentration times volume gives you moles. Oh, yeah, thanks. All right, so you do this, and I don't have the numbers right with me, but you come up with that essentially the HCl is limiting, I believe, right? Yeah, we have that handy. I know what the numbers look like, I just don't have them offhand, so let me see if I can. Yeah, so you get about, you end up with about, 4.2 times 10 to the negative 5 moles of this, and 2.4 times 10 to the negative 5 moles of that. All right? But based on the stoichiometry, you need double this, right? All right, fine. Close enough. Okay. 2.36. Anyway, based on this, you'd multiply this by 2. So if you have 2.4 here, you should need 4.8 of this, right? But you don't have 4.8 of this. You have 4.2 of this. So this one's limiting, which means there's going to be extra magnesium hydroxide. So magnesium hydroxide is left over to the tune of about 0.3, right? Somewhere around 0.3 moles left over. Because you need, yeah. Oh, sorry. So that would be 3 times 10 to the negative 6th moles-ish left over, something like that, right? So you needed, if this is the limiting one, that means that you need 2.1 of this. You actually have 2.4, so it's something like that left over. Okay, this one was widely missed as well, I think because of this first one that I asked. True or false, a mixture of these gases at STP has a volume of 22.4 liters. False. Why is it false? Because there's 2 moles of it. Right. So why didn't you guys get that Monday night? A lot of people put so this is false. right? Yeah, the volume is 44.8 liters because it's 2 moles. And both gases have the same average kinetic energy? True, right, because they're at the same temperature. Yeah, true, they're at the same temperature. They'll have different velocities because they have different masses, but the same average kinetic energy. Yeah. Okay. All right, and then this one, which was, I think a lot of people just ran out of time by the time they got to this one at the end. But this was literally exactly the same thing you did in lab at that antacid lab. And if you can't do this sort of thing, it means you're leaning on your partner a little too much in doing your lab calculations, because you really need to be individually responsible for these. But this is saying based on the titration, so this was like the last part of the exam, and this is a simple titration question. You've got this much sodium hydroxide. Anybody know that one offhand? Yeah, that's... oh wait, I'm looking at the wrong side. Uh, 0.0149 moles. Okay. And then for the HCl, how much you started with, you put in 0.0243 liters. So that means initially you had 0.0248 moles of HCl. Okay. Now the moles of sodium hydroxide used in the titration are how much HCl was how much was left over after the neutralization. So the amount that was actually neutralized is a subtraction of those two. So 0.248 moles that you started with of HCl minus 0.149 moles, we can say left over, comes up to about 0.0099 moles HCl neutralized. By the antacid, yeah. Okay. And then the oxidation state of each element here. Got to remember those rules, right? Let's start with the easy ones first. What's O2? What's the oxidation state of oxygen in O2? 0, right. Okay. What's the oxidation state of hydrogen in CH4? +1. +1. And what must the oxidation state of carbon be? -4, right. And what about carbon, or what about oxygen over here? -2, and carbon +4. And then the oxygen here, -2, and the hydrogen +1. Okay, so this was a widely missed question when it asked which atom was oxidized. Which atom is oxidized here? Carbon. In fact, it's carbon and oxygen are the only ones that change. Carbon loses a bunch of electrons, and oxygen gains a bunch of electrons. I think, I don't know, but I think that where people went wrong here was thinking that CH4 hydrogen is -1. And why do you think that? Because the hydrogen is listed second, and often the thing listed second is negatively charged. But that's not always the case. That's not always the case. You have to use those rules. According to those rules, hydrogen is number 2 after fluorine. So after fluorine, hydrogen is almost always +1. Fluorine is almost always -1. And hydrogen is always +1 as long as it's in a compound with other nonmetals. So that's the next one on the list. You have to go to hydrogen before you go to carbon. In fact, carbon's not even on the list because it changes its oxidation state so often. 2, I think whatever it adds up to, 2, I think. So it's 10 total, yeah. Let's see. Yeah, what?
Initially it was 15 points.
Yes. So it's 10 points for the quiz, and then it's scaled to 15 for the exam.
So 5 extra marks on the exam?
No. Like, whatever you get on here, multiply by 50%, and then that's how much it scales up to for the total. What? Yeah, of course. Yeah, that's why they're written out. Yeah. Okay. All right, let's move on. If you added, I mean, why would you add? What are you showing from him adding it?
Because adding's just so much prettier than
Okay.
on the first one.
So the first part of chapter 8 probably felt to you, maybe should have felt to you, like it kind of doesn't matter. We went through all this stuff. We figured these electron configurations, these valence electron configurations. I don't know if anybody noticed, but we never really talked about why that's important, why anyone cares what an electron configuration of an atom is, why it should matter in any significant way. And so now we're going to actually answer all those questions. The reason that it matters, now before we get into some specifics, the reason that it matters is that atoms with similar electron configurations behave in similar ways. And that was a major, major discovery a long time ago, led to the discovery of the periodic table by Mendeleev, that you could actually predict which elements hadn't been discovered yet, because you knew that this one had this property and this one had this property and there was this space in between. And sure enough, they predicted all these elements that would later actually become reality. Like people would find them and they would be completely right in those properties. So we're going to use the electron configurations we came up with and the idea of counting valence electrons to come up with and predict properties of elements. And in fact, that's mostly what we care about in chemistry anyway, is how do we predict what's going to happen when a different element is used in a different way or something like that. So, first thing we're going to talk about is very basic. It's ionization energy. And we're going to get into some other factors as well. And what we're going to ask here is, how can we predict the ionization energy of an element, not numerically, not like we're going to calculate it from first principles, but how are we going to predict it based on others that we know? So the questions I'm going to ask you are things like, does sulfur have a higher ionization energy than phosphorus? Does oxygen have a higher ionization energy than carbon? And why? And that's going to become important. Those kind of questions are going to become important in the second part of the class. So first of all, ionization we've already talked about. It's when an electron is removed from an element. There was a question on the exam about it. We did a practice question when we talked about the hydrogen atom. You give it enough energy so that you're not just promoting it from one energy level to another, you're actually ejecting it from the atom, giving it enough energy to leave the atom. And you can do this successive times with elements that have multiple electrons. So, as you imagine, or as you see here, aluminum in its elemental state can lose an electron. All right? And to do that, you have to put in 580 kilojoules per mole. Now note that measure, kilojoules per mole. In the previous chapter, we were looking at exactly the amount of energy to remove an electron from a single atom. But now we're talking about how much per mole of atom, because now we're looking more at a practical consideration.
Is that only for aluminum or is that for everything?
That number or the unit?
Number.
The number is just for aluminum. So we're going to see a lot of different ones. What you see for aluminum is the first electron takes this much energy. The second electron takes this much energy. The third electron takes this much. And then the fourth electron all of a sudden takes a huge amount of energy. Those are big numbers, by the way, in terms of energy. That's a lot of energy. So we have to figure out, looking at the electron configuration, why do we see that pattern in that way? So there's a big jump from the first to the second, and there's another jump, but not enormous, from the second to the third, and then there's a really huge jump from the third to the fourth. And looking at the electron configuration, we should be able to figure out why that is. So here's the electron configuration for aluminum down here. 1s2, 2s2, 2p6, 3s2, 3p1. Or, more clearly, neon, and then the valence electrons are 3s2, 3p1. So we're going to talk about some things like shielding, which we've mentioned, but we're going to kind of reiterate. And how, let's see what we say, the effective nuclear charge, how an electron feels the nucleus. So the first electron takes the least amount of energy to ionize. Why is that? Well, that's a 3p electron, right? The first electron, the outermost one, the one that comes off first, is a 3p electron. That's farthest from the nucleus, and therefore it's the highest energy, meaning that it's not stabilized as much by the interaction with the nucleus because it's too far away and it's too shielded by all the electrons in between. So it doesn't have as strong a, you could say, relationship maybe with the nucleus, and therefore it's higher energy and it's easier to rip off. Okay. The next one in is now we're moving to the s, and so there's a big difference there between that outermost p electron and now we've jumped to the s, which we know the s orbitals are closer to the nucleus than the p orbitals are. So the closer nucleus s orbital is now losing its electron, takes a little more energy. The third one still takes more energy yet, but it's not quite as big of a jump because that's just another s electron. You're removing another electron, which always is harder, but you remove it from the same orbital. So then what's to explain this enormous jump in between the third ionization energy and the fourth ionization energy? Yeah, what was that? You're jumping from S to P, but yes, that's true. And also, you're jumping shells, right? So the other three electrons were all removed from the n equals 3 shell. And then the fourth one has to actually be removed from the n equals 2 shell, which is a core electron. So those electrons are held very tightly and are going to take a huge amount of energy, like 11,600 kilojoules per mole, to actually remove. So these things that I'm saying, these are the kind of arguments that I want you to make when I ask you things like, why is this energy higher than this? So let's look at some other ones. Here's a chart. Let's see if I can zoom in on this a little bit for those of you who don't have it in front of you. Yeah.
Is there any way to calculate how much energy, or is it like you're supposed to know?
You don't need to know. You don't need to memorize the numbers. You can always look them up. They can be calculated using like fancy computer programs and stuff. Mostly they're experimentally measured. You can do high energy experiments where you rip off these electrons and you calculate how much energy it takes. So here's a neat table from your book talking about the ionization energies. So first, let's look at aluminum. Okay, and they've color-coded this here. Aluminum's right here. There are those first three ionization energies. And then once you jump into those core electrons, the energy goes way up. All right. So the blue is all removing valence electrons, and then the pink is what happens when you remove a core electron in those atoms. All right. So the other thing to note, that's going this way. That's what we've already talked about. That as you get closer to the nucleus, those electrons are harder to ionize. The other important trend is looking what happens when we go across the periodic table. So you'll see here, going from sodium to magnesium, there's an increase. Then there's a drop at aluminum, an increase to silicon, an increase to phosphorus, a little drop to sulfur, and then an increase to chlorine, and an increase to argon. So first, let's talk about those overall trends, and then we'll talk about the little drops and the little exceptions. Here's it in graph form. That's kind of what it looks like. So as you move across the periodic table, the ionization energy roughly goes up, meaning the first ionization energy, meaning the energy it takes to remove one electron from an atom roughly goes up as you move from left to right. Why do you think that is? Yeah, the nucleus has a stronger pull on them. As you go across, you increase the number of electrons, but you also increase the number of protons. So the nucleus has a greater charge as you go from left to right. And that increases that pull on the electrons and makes them lower energy. So that's why the things on the right will have higher ionization energies than ones over on the left. There's other parts to that too. Why does it sort of reset? Why do you get the highest ionization energies with the 8A atoms, the noble gases?
It's full shells.
That's right. They're full shells. They have a full valence shell. And so one thing to keep in mind as we start talking about this stuff, we should write this down. Full shells and half full shells are generally more stable. Now, full shells are much more stable. Half-filled shells are a little bit more stable. And that's true for subshells as well. Okay, so now, now let's look at some of these exceptions. We talked about why the ionization energy broadly goes, or roughly goes up as we go across. But if we look now specifically, it doesn't go up the whole time. It goes up and then down, and then up and then down, and then up again. What's to account for those little blips that go down instead of up? Let's look at them individually because they're actually slightly different reasons.
They get like full S shell and full P shell.
That's right. So when you see, let's start at lithium for instance. Lithium, here's the energy, then it goes up to beryllium, and then it goes down to boron. And that's because lithium and beryllium, we're talking about ionizing 2s electrons, and suddenly at boron, we're talking about ionizing a 2p electron. And a 2p is a little bit less strongly held than a 2s. So it's a little bit easier to rip apart, actually, than the 2s. Even though it's being held more by the nucleus because of what we just talked about, it's actually easier. It ends up, if you add it all up, being easier because it's in the 2p. So then you got 2p, 2p, 2p. And then we have a little blip down again when we get to, that would be a nitrogen, right? So, or oxygen. So we got boron, let's list these here. I don't get confused. You got boron, carbon, nitrogen, and then when you get to oxygen, it's a little bit lower ionization energy again. What do you think explains that? The half shell thing, the half subshell thing, right? You can fit 6 electrons in p orbitals. So if you got 3 of them in there, that's a reasonable. I'm not going to say it's a stable, but it's a little bit more stable configuration. So that 4th one is a little bit easier to ionize because it pops it back to 3. It pops it back to half full when you take it out. And that explains the exceptions going all the way across. You'll notice in every row, you have these little blips. They become a little bit less important and they get complicated by the transition elements, but roughly they have that blip. Okay. So those are the exceptions to the ionization energies. Any questions there? All right. You also see, it's harder to see from this graph, but there's a slight downward trend in ionization energy as you go this way, which is, what's that way? Like this. That's down the periodic table, right? And I don't know if I put the picture in here. I guess I didn't. Let me pull the picture up from the book. Here's a picture from the book. So you can actually see the trends across and down. So you'll see as you go across, we talk about how it goes up, but with those little blips. As it goes down, the energy goes down. So now, why is that? I've given you all the reasons. It's all the same reasons. Why do you think that the first ionization energy goes down as you go down a column in the periodic table? But if it has more protons, it should go up, right? It should have a greater nuclear charge. It should make it go up.
The shells are further away.
That's right. The shells are getting further and further away from the nucleus. So yes, you're increasing that nuclear charge, but the shells are getting further and further away, making it easier to pull those electrons off. So they have less of a pull into the nucleus. All right, and that's why you get those trends. So what should you be able to do about ionization energy? You should be able to answer questions like this. So for these two, I want you to think about them. I want you to try to write something down. First, silently, by yourself. Then, for both questions, then once you have answers for the first two questions, then talk to the person or people you're sitting around and ask them what they think, what you think, and see if you can discuss it and come to some kind of a conclusion. It has to do with this half shell thing. A half shell is particularly stable because none of the electrons have to be paired. And there's an energy cost associated with pairing electrons. So when there's just 3 electrons, that's relatively stable. And when there's a 4th electron, it has to pair with them. So that 4th electron becomes easier to take out than one of the 3. All right. So going from a just more than half-filled shell to a half-filled shell is easier, that is less energy, than going from a half-filled shell to slightly less than half-filled shell. Okay. Yeah. So let's try it out here. Let's use the boxes. For phosphorus, that's in the 3rd row. We've got 2 electrons in the 3s and 3 electrons in the 3p. And they're going to be spaced out like this. Okay? Then for sulfur, we have 2 electrons in the 3s and 4 electrons in the 3p. Okay. So ionizing sulfur means removing one of those 3p electrons and removing the 4th one, bringing it down to 3. Ionizing phosphorus means also removing a 3p electron, but moving it from 3 to 2. And so that's going to take a little bit more energy. Now notice, that difference isn't huge. It's the important thing is that it's the opposite of the trend that you would expect. All right, next one. Here are 3 atoms. We don't have to say what they are, but what are they?
Sodium.
What's the first one?
Neon.
Neon, sodium,
Magnesium.
and magnesium. Right. Okay. We'll do these separately. Which atom has the largest first ionization energy? The largest first ionization energy. Neon, right. It takes the most energy to rip an electron off of neon because it has that nice stable full shell. But also, we should look at these and see that the electron coming off in each of these cases is a 3s electron. And the electron coming off this is a 2p electron. And whenever you go from a higher end shell electron to a lower end electron, the higher end one is going to have a much lower ionization energy. That is, it's much easier to take out an electron when it's far away from the nucleus than when it's close into the nucleus. Okay. So let's extend this question a little bit. Rather than having saying which atom has the largest first ionization energy, let's actually rank them all. From lowest to highest, IE1, which is the first ionization energy. So what has the lowest first ion? Well, we already talked about which has the highest. That's going to be neon, right? What has the lowest first ionization energy? Which of those? sodium will have the lowest, right? Because you're taking out just the one 3s electron and moving it back to a full shell. And then the magnesium one will be in between. This is a question that you'll see a lot, this type of a question, in terms of both my exams and the final. Rank things in terms of ionization energy, which is the proper ranking of first ionization energy, of second ionization energy. And to do those, all you have to do is look at the electron configuration and figure out which is the electron they're talking about and what happens when you remove it. So, second question. Which one has the smallest second ionization energy? That is, yeah, so it's magnesium. That's the second, removing the second electron. Now, removing the second electron is always harder than the first. It's always more energy than the first. But which of these three has the smallest second? It's magnesium, because that second electron is coming out of the 3s and making it a nice, stable, full shell. Whereas the second electron from sodium is actually coming out of the core, and the second electron from neon is coming out of the same place. All right, so that's ionization energy.
Can you rank this like ionization?
Yeah. So for the second ionization energy, the highest second ionization, or I'm sorry, the smallest second ionization energy, the one we just discussed, is going to be magnesium. So then what do you think is going to be higher ionization energy? The second of neon or the second of sodium? Why? Somebody who said one, why do you think?
Sodium for the full shell. Yeah, you have to go in the second full shell.
Yeah. Yeah, so it's actually, let's see if we can find it here. Right? It's actually going to be fairly close. That's first ionization energy. Yeah, magnesium will certainly be the smallest. I believe I don't know. I don't know the other two. We'll have to look it up. But that's a tougher thing to know, because in both cases, you're removing an electron from a core electron, basically. My guess would be that the sodium's second is the biggest, and the neon's second is smaller, because the sodium one, you're actually first breaking into that full shell of the core shell. But I'm not sure that's true, so maybe. Okay. Now, ionization energy talks about taking an electron out. Electron affinity is kind of the opposite. What happens when you put an electron in? Now, electron affinity is not electronegativity, which is something we'll talk about. I don't think we've talked about that yet, right? We'll get to that in chapter 9. Electron affinity is how much energy is released when an electron is added to an atom. So adding an electron is usually an exothermic process. It releases energy, whereas ionization is usually an endothermic process. It requires energy. So in these electron affinities, you'll notice they're kind of all over the place, right? You've got some negative ones and then these ones that say greater than 0. In those, the reason that numbers aren't actually given there is when the electron affinity is greater than 0, you basically say there is no electron affinity. If it costs energy to put an electron in, that thing is not getting an electron. With some exceptions, as everything has in chemistry. But the point here is to look at these numbers, and the ones that are more negative mean that more energy is released when an electron joins. So for instance, this row has very, very largely negative electron affinities. Why do you think that is? Based on electron configurations.
Because you need one electron to make a full shell.
Exactly. If any of those atoms get one electron, suddenly they have a full shell. So that's going to release a lot of energy, make it a lot more stable. That's why chlorine gas is a poisonous corrosive gas, but Cl minus chloride ion is something that's in water and all around us. It's a more stable situation. Once again, we can look at trends, and we can see a couple little exceptions. So one trend we see is going this way, the electron affinity basically increases. I mean, it's negative, so it's hard to say stuff like that, but the energy is greater. Greater negative, do you understand what I'm saying if I say that electron affinity increases? It's a negative number, but the number itself is getting bigger. The magnitude of it is getting bigger. So that's roughly true because, as you know, as we've just talked about, as it gains those electrons, it gets closer and closer to having that full shell. Now the big exception is in this row here. So everything looks great. It's getting bigger and bigger, bigger and bigger. Actually, in these two rows, all of a sudden it gets way lower, and then it goes back up again. So what's special about those two rows? Let's start with this one. What's special about this one? Row 2A. Why does that not go up? In other words, what is happening when an electron goes into one of those atoms? Where does it go? Yeah, it has to go into a new subshell. So here you have, so like in this column, column 1, you have one electron in the valence, right? It's in the S. So if you add another one, yeah, you're pairing it up, but you're still just putting it in the S. It's fine. It should be decent, right? Now you're taking an extra electron from like magnesium, which already has its full 4s or 3s, and you're putting it in the P, right? So you're adding it into a new shell, and there's no real energy. That's not really energetically favorable to put it in the new shell. The finishing up the S was good, but putting it in the new P doesn't really help you. What about this exception? What's happening there? What do you think based on what we've been talking about? Yeah, it's the half thing. All of these electrons are already half full. So if you put one additional electron in, you have to pair them up. And so that's the major trend here. You'll notice the other direction going up and down the rows is not so simple as it was with ionization energy. It's kind of all over the place. It kind of goes up a little bit and then down, goes up and then down. This one just keeps going up. This one goes up and then down. That has to do with the D electrons and where they come in. Yeah. Because it's what? It's completed the subshell, yeah, the S subshell. And then the next electron would have to go in the P, so it would have to kind of start a new one. That's really far away from the nucleus, so there's not much, you're not getting back much energy by putting an electron there. So I have on these notes, the EA decreases down a group. I'm going to put parentheses in here and say, sort of. That's not a very reliable trend. The other trend, yeah. We can talk about it, we can explain it. This decreasing down a group, that's only true for some groups, unfortunately. Okay, let's stop there and we'll take a break, and then we'll come back and talk about size, atomic and ionic radius, and I'll go get your exam. All right, one of the things I mentioned earlier was how you could sort of predict properties of elements based on this idea of arranging them in this way. And this is what Mendeleev did. Initially, when he was coming up with this periodic table, he predicted that there's some kind of element that's beyond aluminum. He called it eka-aluminum, which means like beyond aluminum, or extra aluminum. He said there should be this thing, and based on what we've seen between like boron and aluminum, there should be this other element that this is the properties it should have. He guessed that it was about 68 atomic mass units mass, and this is what it actually is. So, right, pretty close for not having ever actually seen it. That it would have a low melting point, which it does. It pretty much melts in your hand. It would have a density of 5.9 grams per cubic centimeter. That's exactly what it has. Yeah?
I think number 19 is wrong.
What? Number 19 where? Oh, okay. Oh, yeah. So he actually predicted all this stuff. And the same thing with what ended up being germanium, which was what he predicted as being after silicon. Pretty much got these properties right. So that's what we can also use to predict some things about these things. This already. But you know that first column usually makes +1 ions. The second column makes +2. Well, now you know why that is, right? Because you remove that electron and you end up with a full shell. Or you remove those 2 electrons and you end up with a full shell. We can make similar predictions on the other side of the table. Aluminum is commonly 3+. Same reason. Those electrons are easiest to ionize and they give you a full shell. And then these other elements actually want to gain electrons so that they can get a full shell, get what we call a noble gas configuration. So that's a big driving force of a lot of chemistry. And that's where this term periodic comes from, is we can actually, it's cycles, that as you come around the same part of the cycle, you see an element that has similar properties. So yeah, they get bigger, they start to look different, they do some different things, but chemically, a lot of the elements as you go down make the same types of compounds. But here's what we mean by atomic radius. We know that electron clouds are not hard shells, they're not orbits, they're these probability density, these more like fluffy cloud type things. But how we measure a size is we actually take a sample of it, a solid sample of something, and you can measure the distance between the 2 centers, because when you put all of the orbitals together, what you have is roughly a sphere. All the orbitals in an atom together, it's roughly spherical. And now, using a technique like scanning tunneling microscopy, you can actually see those individual atoms, and they do kind of look like spheres. So the radius is the distance between the center of those 2 spheres. Later, in the next chapter, we're going to talk about a covalent radius, which is the radius between 2 atoms that are bonded together. And that's going to be a little bit smaller, because when they bond together, they actually get a little bit closer. So you got your van der Waals radius, or your atomic radius, which is this thing. It's like separate atoms, but as close as they can get together. And then you have the bonding or covalent radius, which is things that are actually bound together. And we won't really get into that one until the next chapter. So, okay. So let's look at some of these and try to explain them. Here are some figures from your book where you talk about an atom and its cation. So you got, let's first go across period number, period number 2. We got lithium, beryllium, and boron. That number is in picometers, which is 10 to the minus 12th meters. And you see that lithium is a little bit bigger than beryllium, which is a little bit bigger than boron. Don't worry about the ions right now, just the atoms. Why do you think that is? Why does the atomic size go down as we go across the periodic table? More protons. How does more protons make the atom smaller?
The more protons you have, the more pull it has on the electrons, so it pulls them in.
That's right. So we have a similar idea that you have more similar to the ionization energy. When you have more protons, you're pulling the electrons. You have a stronger effective nuclear charge in the electrons. You're pulling them in more strongly. And so you have this contraction as you go across. Even though you're adding more electrons, you're pulling them in tighter, and you end up with a decrease in the atomic radius. All right, now what about when we go down a column? So you can see as you go from lithium to sodium to potassium to rubidium, the ionic radius gets much, much bigger. So why doesn't that logic hold anymore? Because as you go down, you also significantly increase the number of protons. So why don't you see a similar contraction going down? More shells, right? Each shell, each time you go up an N, those electrons have a larger probability further away from the nucleus. So as you go to the 2 shell, then to the 3 shell, the 4 shell, those electrons end up taking their time more further away from the nucleus, and that ends up with a larger radius. All right. So you see kind of a pattern here. You can look at the electrons, you can talk about how the nucleus pulls on them or doesn't, and you can explain a lot of these factors that we're talking about. Now let's look at the ions. You'll notice here that each of the positive ions are much, much smaller than the neutral ions. Why do you think that is? There's a couple of reasons, actually. Why is a positive ion smaller than its neutral atom?
You lose a whole shell for one, so then you're down to
Right. So notice each of these ions are actually, they're not the same charge. So you have a 1 plus, 2 plus, 3 plus. So in each case, you're losing all the valence electrons, and you're down to a smaller shell. So that's a big decrease in radius. And then additionally, you have this idea of the pull from the nucleus. As you lose electrons, the protons are not as balanced out, and so the nucleus can pull even more strongly on the remaining electrons. So you end up getting quite a contraction. So cations, positively charged ions, are pretty small usually. And that trend continues also. You see here, whoops, that as you go down a column, you increase in radius of the ions. And as you go across, you increase in radius also, or you decrease in radius just as you did with the atoms. We can make similar, though opposite, conclusions for the anions. As you add electrons, you get bigger. Now, it's not because you're adding them in a new shell. They're still in the same shell. But now the nucleus can't pull as hard because there are more electrons kind of outbalancing or outweighing that nuclear pull. And so there ends up being kind of a whole expansion of the whole atom when it becomes that anion, or the whole radius. And then the other trends also apply. So if we put this kind of all together, let me zoom out here. I put these next to each other for a reason, because they actually, if you just look at the gray ones, which are the atoms, that is picture of going across the periodic table, and you do see that contraction happening all the way across. If you want to see kind of how everything is arranged with that, here's a table that shows the atomic radii of all of the elements, well, most of them. And you see the same kind of thing. So there's a big jump up in radius every time you go to the next period. And then as you go across the period, you go down in radius. And then you kind of jump back up. The transition elements get a little funky in there. But mostly, whoops, so we can also look at this type of a bar graph. It's a little harder to see because the differences aren't that big. But those are the general trends in atomic radius. All right. So the last thing we need to talk about, which I don't think I have on here. Oh, well, let's do a problem of that first. Predict the trend in radius for the following ions: beryllium, magnesium, calcium, and strontium. So just as before, look at those ions. They're all 2 plus. Don't look at the numbers from the previous page. Use your brain. Figure out the trend in the radius, and then justify it. Why does it do that? Why is that the trend? Do you have a question? Okay. predict the trend in radius. Is it going to increase? Is it increasing or decreasing? Well, they're all the same, but I'm saying as you go from one to the other, do the radii increase or do they decrease? Yeah. Yeah, it's a comparative question.
So going across the period?
All right, so what do you think? What's the trend?
Bigger.
It goes bigger as you go from beryllium to strontium? That's right, why?
Going down.
That's right, because you get a new shell with each one, and they get further and further away from the nucleus. So that's the trend on an ionic radius. Now, I'm going to ask you about this, like on your quiz next week, or on the future exam. I might say something like, why does magnesium have a bigger radius than beryllium? So why does magnesium have why does Mg have a bigger radius than Be? A lot of times what people say is, well, because atomic radius increases as you go down. Why is that not right? That's just stating exactly what I said. Why is this thing bigger than this? Because it's bigger than this. That's not a reason, right? That's not a reason, but a lot of people say that. The reasons are the things that you all just said, that it increases in shell, and so the next shell, the electrons are further away from the nucleus, right? That's a reason. That's something, some physical reason that accounts for this trend. Don't just say, well, the reason is because of this rule that I memorized, that things get bigger. That's not really how it goes. The trends are useful. It's useful to kind of have an idea that, oh, it gets smaller as you go across or it gets bigger as you go down. But you need to know the reasons behind those rules also. So things that we can now predict. One thing we can predict are reactions of alkali metals. What are the alkali metals? The first row, group 1, or 1A. These metals react with water, for instance. And because of their periodic properties, they actually all react kind of the same way. You take one of those metals that's a solid, and if you expose it to water, actually, I have to do it like this, you will form the metal hydroxide and hydrogen gas. What type of a reaction is that? Of those types? What? It's a redox reaction, yeah? What's getting oxidized? The metal, and what gets reduced? In a redox reaction, there always has to be something getting oxidized, something getting reduced. So if the metal's getting oxidized, what gets reduced? Hydrogen. Hydrogen. Hydrogen goes from +1 in water to 0 when it's all by itself. So that's gaining an electron. And this is true for any of these. So like sodium reacts with water, actually fairly violently, right? So I can get a picture of that. True, depending on your definition of better. Here are some pictures in the book. You drop these things in water, they all react, forming hydrogen gas. Lithium kind of sputters around, makes a little hydrogen gas. Sodium will start to flame, and potassium will make quite a violent reaction. And rubidium and cesium even more so. But they all kind of do the same thing. That's the idea of periodic properties. Now, why do you think... So here's the big question then, based on all the stuff we've talked about and that reaction I just showed you. Why do these reactions become more and more violent as we move down the periodic table?
It's easier to pull the electrons away.
Right, right. It's easier to pull that electron away as you get lower down, right? So you end up more easily ionizing it, and more easily, another way of saying that is a more or a less endothermic process. And since the other side of this, actually the reduction, the formation of hydrogen, is exothermic, that actually ends up outweighing it, and that's why you end up with this big explosion.
Do we notice that?
No.
Are you doing Chem 2?
No. In fact, we don't even have these here. We do have sodium, but we don't, and lithium, but we don't have any potassium around. In graduate school, I saw an entire room burned to the ground from rubidium. So, not on purpose. Not on purpose. It wasn't good. What? M means all of them. Any of them. Any of those group 1A elements. So, put in whatever one you want there. Sodium, potassium.
Was it a professor?
A student.
They get kicked out of college?
No.
Oh.
So they get charged.
No. But it was quite a character. What do you think that means? Whoops, only one T in metallic. Yeah, having the characteristics of a metal. What are the characteristics of a metal? Malleable, you can hammer it right into sheets. It's usually shiny. It's conductive. What? Yeah. It conducts electricity. The metallic character is actually not a binary thing like we've sometimes said, that this is a metal, this is not a metal. It's a trend like anything else. Some things are more metallic, have more metallic character, some things don't. Well, generally, let's make our periodic table here. Metallic character decreases. Which way would you say? To the right or to the left? Decreases. To the right, because all that stuff over there is the stuff that's not metals, right? So it decreases across this way, also going up. Things at the bottom are more metallic than things at the top. Okay. And actually looking at pictures of some of these elements, which the book has, is a fairly striking way of showing this. You can really see whether something's a metal or not just by looking at it. So you got sodium, clearly metallic, magnesium, aluminum, we've probably all seen these things actually. Silicon is not exactly a metal, but it kind of looks metallic, so it's kind of in between. Phosphorus definitely doesn't look metallic, it's kind of just a dull powder. And sulfur is a bright yellow, waxy looking thing, certainly not metallic, and then chlorine is a gas, definitely not metallic. So you can see that kind of in action. And you can also see it going down the periodic table. This is a neat set of pictures too. You've got nitrogen gas up here. Oops, nitrogen gas up here. Then phosphorus again. Arsenic starts to look a little bit metallic, depending on the form that it's in. Antimony, again, can be somewhat semiconducting, doesn't have totally metallic characters, but it really looks like a metal, and it's shiny and everything. And then bismuth is very metallic. So you can see those trends just by kind of looking at the things. And that's what we talk about with metallic character. So number 76 right here. Arrange these elements in order of decreasing first ionization energy. Chlorine, sulfur, tin, and lead. So they're not all nicely in a column or in a row. You're going to have to make some other decisions. I'll write them down for you in our notes here. Chlorine, sulfur, tin, and lead.
For example,
Decreasing first ionization energy. So decreasing first ionization energy. So I want everybody on your own to decide, even if you're not sure why, decide on an order that you're going to put in there. And then we'll talk about it.
CL less.
So you think it's just this order?
Yeah.
Decreasing IE1? Oh, we got some argument there. Well, let's look at where they are. So first, remember, the more things are kind of in with each other, the easier they're going to be to compare. So what do you think? Let's see, sulfur and chlorine are right next to each other, right? So that one should be straightforward. Which one is going to have a larger ionization energy, chlorine or sulfur? Chlorine, right? Why? Okay, yeah, all that's true, but the best answer there is to, again, talk about how it's attracted to the nucleus. As you have more protons, you increase that effective nuclear charge, you increase that pull, and so it's harder, it takes more energy to remove that electron. So we know chlorine is going to have a greater electron affinity, or ionization energy than sulfur. Okay, let's look at the other two. Tin and lead, right on top of each other. Which one there has the greater ionization energy? Tin. And why?
different shell.
Yeah, different shell. So lead has a lot. Lead's first ionization energy is taking out a 6p electron, whereas tin's is taking out a 5p electron. And so a 5p electron is going to have a stronger interaction with the nucleus. So tin is greater than lead. Now, let's look at, because we know if chlorine is less than sulfur, or chlorine is greater than sulfur, and tin is greater than lead, let's see if we think tin is going to be greater than chlorine or less than sulfur. So what do you think? Probably less than sulfur, right? Because it's like 2 shells away. And we know that that moving to a different shell has a pretty big effect. Because tin, you're taking out the 5p, and sulfur, you're taking out the 3p. So that's a pretty big, that's 2 shells of difference. So we should probably put that, well, right where it is, right? So the lowest ionization energy will be lead, and the highest will be chlorine, and the other two are in that order in between. But those are the kinds of questions that you ask when you see these. Many of these questions won't have things straight in a line or in a column on the periodic table. So you kind of have to ask yourself, well, which one is more than the other? Okay. What? All right. So one more. Let's try this one. 78. What? That's right. So chlorine has the highest ionization energy. It takes the most energy to take an electron out of chlorine, because there's more protons pulling those electrons in. All right, take a look at this one. You got 4 successive ionization energies. So you're taking one electron out, then a second one, then a third one, then a fourth one. Which element in the third period do these ionization values belong to? You should be able to tell based on the ratios there, or the jump between one and another. So what do you think? Why aluminum? I know, but but why? if you didn't know that, if you didn't remember that from before, how could you tell that these numbers apply to aluminum?
Because the way they change.
How? I mean, you're right, but you got to be a little more specific.
Yeah, like the way they jump.
Yes.
You can tell because the momentum if you come from like
Yeah.
and you see it when like the biggest jump to 11,600.
Right.
It's doing it when you have the big jump.
That's right. So that big jump there between 2750 and 11,600, between IE3 and IE4, that big jump is when you stop removing valence electrons and you start removing core electrons. So for aluminum, you remove one, you remove another, you remove another, and then the next one you have to remove is actually from the core, from the 2p. And so that takes a whole lot more energy now.
How do you know that that's aluminum but not the D?
You don't, except that the problem says to which third period element.
Okay.
So it's in the third period. Otherwise, yeah, you wouldn't know.
So you 3 to the 4 is going from 3s to 3p.
No, 2p. IE3 is removing 3s1, the last 3s electron, and then the fourth ionization energy is removing a 2p.
I think people kind of like hop down.
Yeah, you kind of hop from one. So you lose one, it's like magnesium. You lose two, it's like sodium. You lose three, it's like neon. And then to lose that fourth one, you have to move actually from noble gas configuration to more like fluorine.
Can you go back to the others?
It's in your book. Okay. All right, there was a request for another problem. The electron configuration of gold plus?
Yes.
Plus one? Okay. So to do these kind of things, these ions, if you're not sure of them, it's helpful to write out the electron configuration of the atom and then take an electron out to find the ion. So gold atom electron configuration, that's element number 79. So we've got xenon, and then you got 6s2, 5d10, 4f14. Oh, right, because we're gold, we're in the middle. Sorry, I thought we were something. So it's 6s2, 4f14. Then 5d, we've got, starting at lanthanum, 1, 2, 3, 4, 5, 6, 7, 8, 9. What? 9, yeah. 5d9. So actually, the configuration I think is probably 6s1, 5d10, just like with copper. But anyway, that doesn't matter here. Actually, it might. So because you can jump one down and make a 5d10, remember the filled shells are especially stable, probably a better way to write this configuration is 6s1, 5d10. So if we remove one electron, where is that electron coming from? The 6s, because that's the outermost. So for gold plus, that one's gone. So it should be, gold plus then should be xenon 4f14 5d10. Okay?
So can you write the electron configuration for just gold? Is that 5?
That's what this is,
Oh. Okay. That makes
with the electron in there. Why isn't it what? There's energy advantage from having a full subshell. Okay? So if you can jump one electron back and fill up the D's, it usually does that. That's right. So, you know, as you go in, you get lower and lower energies with different shells. So filling up a lower energy shell is more energetically advantageous than filling up a higher energy shell. So, yeah. Yeah.
You can still do stuff like that for the half shells?
Yes, although when you get into the second and third rows, it gets a little funkier, and that's why we don't usually worry too much about it. If you look at the electron configurations in the book, let me see if I can pull them up real quick. You'll see this. To go through all the pages here.
So, okay. So the one in red is the gold ion?
Yes.
Yes. So that's this one. Yeah, here's the here's some configurations of transition metals. So you see here, it's very clear. You stick in the 4s2 on the first row, except for those half-filled ones, chromium, and then also over here. Same thing in the second row, although you see it actually jumping down to make 4 in there also, and then here, and then here, and then actually both of them jump down in palladium, and there's a bunch of other weird stuff going on. It gets even weirder down there, so those aren't necessarily predictable. The copper row and the chromium row are relatively predictable, although tungsten's a little different, but you can see here gold, as we expected, does have one jump back. Okay, before I forget, mastering chemistry. There is an error